Hello, everyone. It's me, Billy Younger, again. We've done some work with Maxwell's equations. I used Maxwell's equations to derive a wave equation. And of course, I showed you the general form of a wave equation, a second order derivative in space of whatever's doing the oscillating is equal to 1 over v squared times the second order derivative in time. I actually used Maxwell's equations to derive one of those for the electric field, another one for the magnetic field, and I showed you that basically a plane wave, that was possibly in another video, I showed you that a plane wave satisfied a wave equation provided that the velocity of the wave was equal to the phase velocity, which is omega over k. So now I want to actually use Maxwell's equations and the idea of a plane wave to show you that one, the electric field, the electromagnetic radiation is characterized by an electric field oscillating perpendicular to the velocity propagation. So there's actually a transverse wave, and that the magnetic field is also a transverse wave acting perpendicular, oscillating perpendicularly to the velocity, and that the electric field and magnetic field are in fact perpendicular to each other. So to do that, I'm going to start off by writing Maxwell's equations in general form, and then I'm going to show you them in a vacuum. And then I'm one by one going to use them to make conclusions about the electromagnetic radiation, i.e. the electromagnetic waves. All these waves, of course, are characterized by speed v is equal to 1 over the square root of mu 0 epsilon 0. And as I showed you in yet another video, that 1 over the square root of mu 0 epsilon 0 actually has the units of meters per second, and in fact has a value of 299,792,458, which is the agreed upon velocity of the speed of light. So let's get started by showing you my document cam. So we're going to start off by writing actually Maxwell's equations in their general form. And it's sort of a general form. I'm actually using in the SI system of units, and I'm not using the auxiliary fields, the D and the H and that sort of thing. So really what we have is a divergence of the electric field is equal to the charge density over epsilon naught. This, of course, is Gauss's law. Then I have the curl of the electric field is equal to the negative partial of the magnetic field with respect to time. And of course, that is that is Faraday's law. And that comes, of course, with the Lenz's law, which is about this negative, and it says that an induced EMF will be created in such a way that it opposes a change in flux. Then we have the Gauss's law for the magnetic field, which is del dot B, or the divergence of B is 0. And again, that's Gauss's law, but in this case, it happens to be for a magnetic field. And then we have Ampere's law, as was corrected by Maxwell, and that's del cross B is equal to mu 0 times the current density, plus here's Ampere's correction, epsilon 0 partial of E with respect to T, and that's called the displacement current, even though it's somewhat based upon a discounted theory. But either way, it's that's what we call it, and that is Ampere's law. And again, that's with Maxwell's correction. So that's Ampere's law. Now, what we're going to do is write that again, but this time we're going to write it for a vacuum. So in a vacuum, basically what happens is there's no charge density and there's no electric field, current density. So those two terms are going to become 0, and we get basically del dot E is equal to 0. Del cross E is equal to negative partial B with respect to T. Del dot B is still 0. And then del cross B is equal to mu 0 epsilon 0 partial of E with respect to T. So those are the Maxwell's equations in vacuum. So for vacuum, I've got these expressions. And what I'm going to use is these equations to actually work out what the electric field and a magnetic field for these electromagnetic waves look like. Remember what we found as far as the electric field goes, or excuse me, the wave equation goes for the electric field and the magnetic field was just basically a del squared E or B is equal to 1 over v squared, which turns out to be the speed of light, times the second partial of E or B with respect to time. And we found that v is equal to 1 over the square root mu 0 epsilon 0, which equals the speed of light, c. Okay, so those are some things we're using. I'm also going to make use of the general way we go about calculating divergences and curls. So I want to remind you all that del dot A for any, of course, vector field, the divergence is partial with respect to x of a sub x plus the partial with respect to y, a sub y, plus the partial with respect to z, a sub z. So that comes in handy. What I'm going to do now is go ahead and use that expression, but I'm first going to define a plane wave propagating in the z direction. So a plane wave propagating in z direction and I'm going to say the positive z direction, which ultimately will come into play, but not right now. But that's basically going to be defined as the electric field E is equal to a vector E that's a function of z and t alone. Okay, and what I mean by that is it's propagating along the z-axis in the positive z direction, which I'll come up later. That basically means later on they'll have an argument kz minus omega t. But this does not say which direction the oscillation's in. All it says is that, for instance, velocity is equal to c times k hat. That would be pretty much all you can say. All right, with that in mind, now I'm going to take Gauss's law and I'm going to evaluate the left-hand side. So I'm going to say del dot E is equal to the partial with respect to x of E sub x, which is just a function of z and t, plus the partial with respect to y of E sub y, which is just a function of z and t, plus the partial with respect to z of E sub z, which is just a function of z and t. Again, that becomes, because there's no x functionality here, this is 0. Because there's no function of y here, this also becomes 0. So I can now say that del dot E equals 0 gives me, or implies, that the partial of Ez with respect to z is actually equal to 0. Now, what that means is that if E is truly a function of z and t, then the E and z, or the Ez of t, should actually be a constant in z. We're going to choose, because we're not really interested in uniform fields, we're actually looking for oscillating fields, which is what the wave equation is completely about. We're going to choose the very special case that Ez is in fact equal to 0. So Ez is a constant. Really means it's a constant with respect to z, but in this case we're going to say that is in fact 0. And since the wave was propagating in the z direction, but it has no oscillatory component in the z direction, it doesn't have a longitudinal component, implies. So no longitudinal component. Implies it's transverse. So it is a transverse wave. Okay. Now, without loss of generality, since it's a plane wave, we know, and it's propagating in the direction of z, then we know basically all the oscillation must go in the x and y directions. We can keep our z-axis mounted in the direction of velocity, and we can twist our y and x, or x and y axis any way we want. I'm going to twist it around so that I can now say E is equal to E of z and t, specifically oscillating in the x direction. And I'm going to go further and go ahead and make use of the fact that it's a plane wave. I'm going to call that E0 cosine kz minus omega t. There's where we just defined it to be going in the positive direction. And I've got a constant E0 that can be evaluated based on initial conditions, but I needed one more constant because clearly that's the second order differential equation. So I'm going to add a phase right there. So that is now what our electric field is. And we can see again, this electric field is in fact oscillatory, propagating in the positive z direction, and it's a transverse wave. So we've already concluded that the electric field portion of the wave equation has given us, in fact, a transverse wave. So now let's use that and go back and apply Faraday's law. So we're going to apply Faraday's law and see what we can conclude about E and the relationship to B. In order to do that, I'm going to first remind us that the curl of any particular vector field A can be given by its ith component being equal to the Levi-Cevitov tensor epsilon I j k times the partial with respect to the j variable, which of course, if j is 1, that would be x. If j is 2, that would be y. If j is 3, that would be z, times, in this case, a sub k. Now, remember, we're using Einstein's summation convention, so that means the I is not repeated, but the j and the k are. So I have to take all possible values of j and k. Well, if I is I, then j can be anything other than I, and that literally means 1, 2, and 3. But if you do 1, 2, and 3, and 1, 2, and 3 with k as well, you're going to find there's instances where j and k are equal, and we know that the Levi-Cevitov tensor gives us 0 whenever two of the indices are equal. So we're really only going to get two terms here. One case in which it's a cyclic permutation of 1, 2, 3, and epsilon becomes 1, and the other one which is not a cyclic permutation, and that's going to be epsilon being -1 times that. Again, this is just me doing it the quickest, most efficient way I can. All you have to do is find out what the ultimate result is in terms of x, y's, and z's. You can go back and look at any of my videos on how to compute a curl. I'm just using, like I said, supposedly the shortest way. So when I do this, when I actually try to count or calculate the x component of del cross E, it's done like this. So the x component means epsilon I, the I would be 1, okay? So I'm going to write epsilon 1. This has to be, of course, 2, 3 to not be 0, or it could be 3, 2 to not be 0. I'm going to do 2, 3 because that's a cyclic permutation. That gives me the 1, but the 2 corresponds to the y derivative, the derivative with respect to y, of the z component, which would be ez, which of course we know is 0 because we've made it only the x component. Plus, I'm going to take epsilon 1 again. This time I'm going to do the non-cyclic permutation, which is 3, 2. So this time the epsilon is going to be -1. And in this case, I get the partial with respect to z of e y, which also is 0. So this function right here is 0. This function right here is 0. So the whole result is just going to be 0. That's just the del cross E part. That has nothing to do with the partial with respect to B. I'm just working out the left-hand side right now. Similarly, the partial, or excuse me, the curl of E y component is epsilon 2. Of course, if I want that to be a cyclic permutation, then it has to be 3, 1. Well, that means partial with respect to z of ex, which is the one that's not 0 because remember we defined it to be the x component. Plus, we're going to have epsilon 2, and instead of 3, 1, we're going to flip them and make 1, 3. And of course, that epsilon is going to be -1. but it's going to be partial with respect to x of e sub z. And of course, e sub z we've already discussed being 0. And then what I end up getting is just the partial with respect to z of ex, which is just e0 cosine kz minus omega t plus phi, like that. Okay, so that's actually the y component of the curl. Now I can do the z component of the curl. Del cross E sub z is going to be epsilon z, or actually, excuse me, epsilon 3. Sorry about that. Let's actually make that a little nicer. This looks hideous already. But, oh, that's just nice. Okay, so that'll look a little better. Epsilon 3, whoa. And then, of course, for it to be a cyclic permutation, that has to be 1, 2. And that means we're going to take the partial with respect to x, because that's what 1 corresponds to, of e sub y, which, by the way, is 0. Plus, we're going to take epsilon 3. This time, we're going to reverse the 1 and the 2. And when we reverse the 1 and the 2, we get 3, 2, 1, which is going to be, of course, negative. And that's the partial with respect to y of e sub x. E sub x, of course, is not 0, but the derivative of it, the partial derivative with respect to y, is definitely 0. So I'm going to get the partial with respect to x of 0 minus the partial with respect to y of e0 cosine k, let's make this a square bracket, kz minus omega t plus phi, in parentheses, in the square bracket. And of course, the derivative of this is also 0. So now we've got the left-hand side of the curl, which hopefully y'all didn't miss too much of that as it slid down below the screen. Here it is. But again, we took epsilon 3, 1, 2 being partial with respect to the first variable, which is x, of the second component, which is y, plus E3, or epsilon 3, 2, 1, which is the derivative with respect to the second variable, which is y, of the first component, which is x. Obviously, the y component was 0 because we've decided to only call it the x component. And then the derivative with respect to the partial derivative with respect to y of this function of z and t is also 0. So I get 0 for all that. Now I can take Faraday's law. And from that, I know that del cross E is equal to negative partial B with respect to T. Well, this gives me that, in fact, the first 0, the x component, which came out to be 0, excuse me, this one right here, that is equal to the negative of the partial of Bx with respect to T. Okay, that's not very fulfilling. In fact, that just means that Bx, the x component of the B, supposedly oscillatory motion, is equal to a constant as a function specifically of z, because that's the only other variable it could be since it was related to the z and t of E. We're going to choose, again, because we're not interested in uniform magnetic fields, we're interested in oscillatory, we're going to choose Bx equals 0. And automatically we see that the x component being 0 means it has no component parallel to E, so it must in fact be perpendicular to E. So we've already shown that E is a transverse wave, and that it oscillates. In this case, we chose the x direction and the velocity being in the z direction. And we just shown that the oscillatory electric field in the x direction is in fact perpendicular to the oscillatory B magnetic field because it has no x component. Now we take the next component, which is the y component, which we found was not 0. And in that case, we found specifically that the derivative of E0 cosine k z minus omega t, which I should put a square bracket there as well, and then put a curly bracket here. That's just the derivative with respect to z. Derivative of cosine, of course, is negative sine, and then the derivative of kz minus omega t plus phi is just k. So I'm going to say negative k E0 sine kz minus omega t plus phi is the left-hand side. In other words, I just evaluated the left-hand side of the curl, but this is corresponding to the y component. So the right-hand side will be negative partial by with respect to t. We'll come back and visit that in a second. What we do see, though, is clearly by cannot be a constant. By must, in fact, be some oscillatory thing because the derivative of it is, in fact, oscillatory. And then I'll take the z component. And, of course, the z component of the curl we found was 0. So, again, I get 0 is equal to the partial of b sub z with respect to time. That implies b sub z is a constant. But again, we're talking about partial derivatives, so it's a constant in this case in terms of z, or excuse me, in terms of t, excuse me, and that's what I should have set up there as well. Sorry about that. That should have been a constant in time as well. But we're not interested in uniform magnetic fields, so I'm going to choose the case where b z is equal to 0. Now we've concluded that B is not only perpendicular to the magnetic field, it also has no longitudinal component. So in fact, it's transverse as well. So I'll just call it TRANSV because I can't fit in the word transverse there. Okay, I will correct these T's. I'm going to actually erase them before I take the photo and put this on my Google Docs thing where everybody can get it. I'll change them back to T and make them look a little neater. Now we're going to attack this equation and see what we can get out of it. Notice we have a negative on both sides. With the negative on both sides, that makes life a little easier. I can drop the negative, and what I'm going to do is I'm going to say partial of by with respect to t, and this is the y component, is equal to k, the magnitude of the electric field E0, times the sine of kz minus omega t plus the phase constant. Now, with that, I'm going to treat it like a separable differential equation. So to do that, what I'm going to do is I'm going to say b sub y is equal to the integral of partial b sub y, but that's also equal to the integral of k E0 sine kz minus omega t plus phi. Again, the phase constant phi. And this time, the partial forces this partial, or this derivative to be partial with respect to t. Now, that's a pretty straightforward thing to integrate. We're actually integrating sine of u, but the u is a function of t, so I'm going to have to deal with that. I'm going to pull the k and the epsilon out in front, and to attack this integral, I'm going to say, let's let u equal kz minus omega t plus the phase constant phi. And then that means partial u is equal to negative omega partial sub t. So what I'm going to need to complete this integral is I'm going to need a negative factor of omega. So I'm going to multiply k epsilon naught by 1 over negative omega, and then multiply this by negative omega to get partial u. And I can carry out my function. Now I'm doing this partial integral, which means I could actually add a constant to it because I have no limits of integration, but that constant is potentially going to be a function of z. That's why I confusedly wrote z up here instead of t. I was getting it confused with the other part. So what I'm going to say now is that by is equal to negative k E0 over omega. So that negative omega I put in the bottom is just so I can multiply negative omega times partial t here to get partial u. So I'm now going to say the integral of sine u, and since I've multiplied by negative 1 over omega, I can already assume I've multiplied by negative omega times this, so it is actually partial u. Now the derivative of cosine is negative sine, so the integral of sine must be negative cosine. So this negative is now going to become a positive, and it'll be k e0 over omega, and I will get the integral being cosine of u, which is k z minus omega t plus the phase constant again. We can see that it's not even out of phase with the electric field because it's still cosine kz minus omega t plus phi, but it'll also be plus a constant that is actually, since we did a partial here, that's actually a potential function of z. Okay, I'm going to choose, again, for the same arguments before, simplicity, and because I don't care about a extra constant term to an electric field, I'm going to choose to make this constant equal to 0. So choose 0. That being said, now I can say that B is equal to, just the y component survives now. So I'm going to say it's equal to K over omega times E0 cosine kz minus omega t plus phi. But remember earlier I told you that the condition necessary for the wave equation to be satisfied is this velocity had to be equal to the phase velocity, the phase velocity, which was omega over k. We know omega over k is of course equal to that velocity, and therefore it's equal to c. So this k over omega is really just, this k over omega is just really 1 over v, which is 1 over c. And of course, this is only the y component, so I'll put a j there. So I'm going to say this is actually E0 over c cosine kz minus omega t plus the phase angle phi, again in the j hat direction. So ultimately what we've learned is that the E and B are in fact transverse waves perpendicular to one another, and since they're transverse, they're perpendicular to the velocity. And in fact, they are E is equal to E0 cosine k z minus omega t plus some phase that we can get from the initial conditions, all of this in the I hat direction. B equals E0 over c cosine kz minus omega t plus phi. In this case, it happens to be in the y direction, and the velocity v is equal to c in the k direction. In fact, if I wish to draw this, I could say, let's let this be our x direction. Let's let this be our z direction. And let's let the axis coming out of the page, which I'll draw this way, I'm going to let that be the y axis. And what I will have then is an electric field that's oscillating in the x direction. If I set the constants just right, so that let's say phi is equal to, let me see, if I let phi equal to plus pi over 2, no, that wouldn't work, plus 3 pi over 2, then I'll basically have cosine being the equivalent of sine, and it's a little easier for me to draw, which is really, at the end of the day, what I care about here. So here's my E0 up here, and again, by choosing phi equal to 3 pi over 2, I get an electric field that oscillates like sine. Again, I'm trying to make this reach the height there. Okay, so that's what our electric field is doing, and it literally means at this point in space, it's got its strongest. At this point in space, it has its strongest, but in the negative x direction. Again, positive x direction, negative x direction, and these points over here are in fact areas where it's slightly weaker, and of course pointing in the same direction as the arrow indicates. that's what the electric field looks like. Now, perpendicular to that, and notice it corresponds to a right-hand rule. It's kind of hard for you to see it, but it has to here. This is in the positive Y direction when this one's in the positive X direction. So in fact, if we let our index, middle finger, and thumb point in mutually perpendicular directions, we can let this one be the electric field, this one be the magnetic field, and the thumb be the direction of velocity. And as long as we're using our right hand to do this, then this right side, our right-handed three vectors actually give us the orientation of E, B, and V, the velocity. So let me show you now what the velocity, or excuse me, what the magnetic field is going to look like. It's going to be in phase. It's going to be like that. Then it's going to go back here and come back there. Then it's going to come out in front again, like that, and then like that, where basically this magnitude is E0 over C, which we might call B0. Okay, so these are actually lying in the YZ plane and acting just like the electric field did, but again, in this case, it's actually pointing in a field in a direction perpendicular to it. This plane, this Y, or excuse me, this XZ plane, by the way, is what we call the plane of polarization. The plane in which the electric field oscillates is called the polarization field. So if you have glasses that are polarized vertically, that means it only allows vertically polarized waves in. Then the electric field would come in easily. The magnetic field would try to be blocked, so on and so forth. But that's really what polarization means. So we've now completed the task, which I advertised, which was calculating the actual properties of the electromagnetic radiation as given by the wave equations. We had one for E and we had one for B that looked exactly the same as this one. The wave equation we derived from Maxwell's equations, which were these guys. Then we used Maxwell's equations, of course, to discern the actual properties of the electromagnetic radiation. And those properties were that the electric field is in fact transverse wave. In other words, it's perpendicular to the velocity. The magnetic field is also a transverse wave. It's perpendicular to the velocity. And in fact, the electric and magnetic fields are perpendicular to each other as well as perpendicular to the velocity, and that they're given by a right-hand rule such that if the electric field is pointing in the direction of my right index finger, the magnetic field pointing in the direction of my right middle finger, then my right thumb points in the direction of the velocity, and that the electric field direction, i.e. the right index finger direction, is the direction of polarization of the wave. I hope that clarifies some things, and I hope that makes it more clear to you that Maxwell's equations do create an electromagnetic wave or suggest the existence of an electromagnetic wave, and that the electromagnetic wave has the properties we just mentioned, and in fact looks like that. Have fun doing physics. Have a good day.